Got everybody. Today we have a very good problem for you guys called search insert positions, right? So this is a very good problem. So make sure to pay close attention to the problem statement, right? So it says given a sorted array of distinct integers and a target value, right? Return the index if the target is found. If it's not found, then return the index of where it would be if it were inserted in the order, right? If we're inserted in order, okay? So we must write the algorithm, right? Or log n runtime complexity, right? So very good, right? So they've imposed that on us, right? Pretty good. So this first example is going to solidify the ask, right? So the ask, so we're given this integer array and this target value, right? And we need to, and we return wherever index the target value is in, right? So okay, C5 is at index 2, right? Got 0, 1, 2, so next 2, we return that, right? Pretty simple case. We just need, we're going to target, find the index of that target, right? So pretty simple. But we run into trouble here, right? So we have target 2, but target 2 is not present here, right? So it tells us to return the index of where it would be if we were to insert it, right? So we know that 2 is within 1 and 3, right? So we would add it there, right? It needs to come after 1 for sure, and before 3, right? So we just go ahead and add it 2, right? And then it would shift everything to the right, to 1, right? So we put 2 index 1, guys, right? And then everything will get shifted, right, accordingly by 1, right? Because 2 was added there, right? Same thing for this one, right? 7 does not exist, so we put it at the end of the array because 7 is larger than any element in the array, right? So pretty simple, right? So how do we go ahead and solve it, right? First example, pretty straightforward. I think we could do a linear loop, right? Let's talk about a brute force, right? We would do a linear loop through the array. If we end up finding an element, right, at an index, right, we find an element that equals to target. Then we go ahead and return that index right away, right? So we check for every index. We would check, does it, are you go to target? Are you go to target? Are you go to target? Then return 2 right away, right? It'll be simple as that, right? It'll be then just a linear loop, right? Linear scan, pretty simple. So how do we handle the cases where target does not exist, right? It will work, right? Because we check 1, 3, nope, none of that is equal to 2, right? So for those, right, we know that we could simply, right, assume the exit condition as well could be if an element is greater, right? So because it's sorted, right? It's a sorted array. As we're going from left to right, right? As soon as we encounter an element that's greater than the target value, right? We can simply return that index, right? Because this is the index of where that target value can be added in, right? And still maintain the ordering, right? So if we had 2 at 3, right? We could put 2 at index 1, right? And then everything gets shifted, right? This will be the index, right? Because that's the first element that's greater than target, guys, right? Yeah, so it's a very good key takeaway to remember, right? So pretty much we handle the 2 cases, right? Where any target's present in the array, right? We check every one of them, and also handle the case where the target does not exist, right? But we end up returning, right? The index of where it would be, right? And we find that by since we go from left to right, we find the first element that's greater than it, then we just add it there, right? Because there's no point in checking the remainder of the array because it's pointless. Because, there's no point in checking it, right? Because those elements, they won't equal to 2, right? To the target because they'll be greater than target, right? So we just focus our energy on finding the first element that's greater than target. They return that index right away, right? And that would be the position where we add it there, and then everything from there, right, gets shifted, right? So we add 2 there and then shift this whole thing here, guys, right? This example will be the same thing, right? We would try to find target if it's not, right? Also trying to find any element, the first element, right, that's greater than it, right? There's no element that's greater than 7 here, right? So it's where we end up returning the length of the array, right, as the result, guys, right? But we can't do linear scans, right? It won't work, right? We need to do a better search, right? Since we need to get that of log of n, right? So that's the search method that's gonna give us the log of n that we need, right? So how do we go ahead and do that? Binary search is going to be very useful here, right? Because it's going to allow us to discard half of the array at every iteration, right? Which is going to make it a lot more efficient instead of checking for each element, right? Worst time, right? We could discard, right? Now waste our energy on particular parts of the array, right? Depending on if it's the middle element is greater than or less than the target, right? So how it's going to work, right? With the prompt similar to that, we would check if the middle element that we're at, right, does it equal to target, right? If it equals to target, we return that middle element, the index of that middle element, right? If not, then we decide, right, depending on, so for example, So how it's going to work, we will check the target, right? Is the target, right, less than the middle element, right? If it's less than the middle element, then I'm going to go left. But no, since this case, target is greater than the middle element, so I need to go to the right, right? We update our left pointer to go to the right. And then we focus our energy on this part of the array, right? And then we check, we do apply binary search on this part. We see that is 5 will be the midpoint, right? Is 5 equal to target equals to target, return the index, right, of 5, right, which is 0, 1, 2. Pretty simple, as you can tell. So this is the end of the case where we applied same binary search, but it does not exist, right? The target does not exist, right? So we apply binary search, we check, is the target less than the middle element? Yes, it is. So I'm not going to waste my time here because all the elements are going to be greater than it, right? So I focus my energy here. Apply binary search again, right? I focus my energy here, right? Apply binary search. And then we check, right? Is target less than 1, right? No, it's not less than 1, so we update our left pointer to go right. And then left pointer is pointing to this spot, right? Right? And this is where we would insert 2, right? This is the position where 2 will be at, right? As you can see, right? The left pointer should be pointing at, the first element, right? The smallest element that's greater than or equal to a particular target, right? So it will point to that, right? So that's kind of what the guarantee that we get here, right? So that's what we end up returning. If it does not exist, right, we return the left pointer, which is the index of where it would be inserted at if we were to insert it, right? We can apply the same algorithm here, guys. 7 is 7 less than 3. It's not 7 less than 3. Nope, 7 is greater than 3. So we go to the right, to focus our energy on that part of the area. We can apply is 5. Is 7 less than 5? No, it's not, right? Then we apply our energy here, right? Is 6, is 7 less than 6? No, it's not. Then we go to the right again, and then that's when we end up at the end of the array thing, right? It crosses over, right? Left. When we go to the right, that's us updating the left pointer, right, to go to the right. So it's already end up returning 4, guys, right? So this is how the left pointer is going to guarantee that we're good once we if the element is not present, the target and the nums array, right? So hopefully it makes sense. So let's quickly cut up the code, right? Real quick. So in mid, it's gonna be sorry guys. So left boundaries and the right boundaries. All right. So we start with the whole array as the start bound. All right, and then the exit condition is gonna be once it crosses over, right? So the midpoint we're gonna calculate it each time. Right, the midpoint is gonna be easy. All right, minus left divided by 2. And then we're going to check, right? Is our middle element, right, that we have right now, does it equal to the target, right? It equals target. Then we are good. We return the mid right away, right? But if not, right, this is where we make the decisions to go left or right, right? Okay. So if nums a mid, if the target is greater than nums a mid, right? It means that we need to go to the right. Okay. If not, that means the target is less than mid, right? So I need to focus my energy on the left-hand side, right? So if target is greater, right, that means that we undershot, so that we need to keep going to the right, right, to find bigger numbers too, right? So if we never enter this case, right, that case where nums equals to target, then our left pointer, right, got our back, right? The left pointer is going to be pointing at the smallest element that's greater than us, right? And which is conveniently the position where we would insert that position, right? And then we'll shift everything to the right, after that, right? So let's see if we pass the small test case. So let's see, it made sense. So it looks good so far. So we're submit. Looks like it was accepted. Everything looks good. All right, So if it makes sense, you gotta know that in the comment section. If you're new here, subscribe to the channel because we'll be doing a lot of other videos just like this one. So I want to thank you guys for watching, and I'll see you guys in the next video.